Hello everyone, today I will talk about VMM and WTA, and my name is Zhiha and my partner is Yang Hang. First thing is about the concept of the circuit, which is VMM and WTA. For the VMM, we package voltage information into a log form and use the log form to generate an exponential current, which makes the current exactly linear to the voltage. So with the output current, we put the current into a WTA circuit, which I think is a multiple road differential pair. So we have a tail current and a P-fed bias. If we increase the P-fed bias, actually it makes this channel easier to to lose, basically, because the output voltage should do not need to be pulled down to supply the voltage for supply the tail current. So if you want to make the channel more easier to win, we will lower its P-fed bias current. And our setup is very easy. It's just because there's already a module in the library, and first thing is we use a union matrix and do like a union input and find out that our P bias is working perfectly. Which for the left picture here, we have the channel 1 of the yellow and the channel 2 of the blue. And you can see when the yellow wins, just wins perfectly, and the blue wins perfectly too. And on the right picture, we have the channel 3 as the blue one, which also wins and according to the truth table. So we adjust it, and then we do like XOR and AND. The first thing we need to do is derive the weight matrix for XOR and AND. So we find out that we have actually two input, but we have another bias to make sure that there is a constant in the equalities. Basically, we want this matrix and times the input vector to generate this kind of truth table for each channel. And then for this inequality, we can generate these constraints. Using these constraints, we can figure out the result weight matrix, which is presented here. We do an experiment for this matrix. Obviously, it didn't work out very perfectly in the first place because we need to further adjust the P-bias current actually. So this is our final result, which is XOR and AND for channel 1 and channel 2. For the XOR output, you can see like for the first 0, 0 and the final 1, 1, it's all high. But for the 0, 1, the 1, 0 in the middle, it's low. And for the end, for the 0, 0, 0, 1, the 1, 0 case is high, but for the last one, 1, 1 is low, which is exactly what we want it to be. And for the channel 3, which is actually a null function, when the output is 1, 1, 0, 1, the 1, 0 actually is high, but for 0, 0 is only low, and the fourth channel is always high. So the problem of this setup is that our output, the first channel, its amplitude is not so the difference is not so stunning. And also you can see when the channel lost, it didn't come to the top, and when the channel win, it didn't go to the bottom, which means we actually set this bias here, the 16, very high to make sure that it don't come this way, but we cannot do that, seems like. But we can achieve differences between the win and lose at always over 500 millivolts. So basically, we can add a comparator to the output of this WTA output, and then we can find out which one is the winner. Okay. Thank you for listening. See you.